Hey guys, this is Professor Janacek. I want to talk about a special power series. I want to look specifically at a Taylor series. Now, first let's recall what a power series is. A power series is really just an infinite polynomial function. It can be written as the summation, as k goes from 0 to infinity, but what makes it a power series, not only is it a series, but I have k raised to some power. That's where it gets its name. So we have a basic power series, but what's special about a Taylor series? Well, a Taylor series takes those coefficients and writes them in a very special form. So we still have a power series, but the coefficient looks like f raised to the k in parentheses of a over k factorial. Now that f raised to the k power in parentheses, that is a notation for the kth derivative of f. We evaluate that at a and then divide by k factorial for the coefficients on a Taylor series. Let's take a look at an example. Let's find the Taylor series for f of x equal to 1 over x squared about x equal to -1. So this is centered at -1. So to begin with, we have our function f of x is 1 over x squared. Because I know I'm going to take the derivative of this, it might be useful to think of this as x to the -2 power. All right, so the first derivative, 1 over x squared, you can go about this a couple of different ways, but in the end, we most likely will use the power rule for derivatives. We end up with 2 over x cubed, or if you'd prefer, -2 x to the -3rd. The second derivative is 6 over x to the 4th, or 6x to the -4th. The third derivative is -24 over x to the 5th, or -24x to the 5th. And I think that might be enough to give us our pattern. Now the next thing we want to do, so that's giving us the pattern for the kth derivative, but now we also have to evaluate that at a. So we want f at -1. So replace x with -1 and we get 1. Evaluate the first derivative at -1. That gives us, let's see, that's what, +2. The second derivative evaluated at -1 gives us +6. Third derivative evaluated at -1 gives us +24. Notice how those negatives go away. And I think that's enough for us to kind of figure out a pattern here. I see it. Let's see if you do. If you don't, let me show you how I'm recognizing a pattern here. This is 1, and this is 1 times 2, and this is 1 times 2 times 3, and then we have 1 times 2 times 3 times 4. So I noticed these were products. In fact, very special products. We can represent this using the factorial. F at -1 was 1 factorial. F prime at -1 is 2 factorial. The second derivative at -1 is 3 factorial. The third derivative is 4 factorial. So notice again that this is the third derivative, which gives us 4 factorial, or the second derivative, which gives us 3 factorial. The first derivative, which gives us the 2 factorial. You can say the 0th derivative, if you will, gives us 1 factorial. But what I want you to notice is the connection between the number we're taking the factorial of and which derivative we're looking at. So you'll notice if I have whatever the derivative is, I add 1 to that, and that tells me what I'm going to take the factorial of. So I think that's going to allow us to come up with our pattern. For the kth derivative, evaluated at -1, looks like we're simply going to take whatever that k value is, add 1 to it, and then evaluate the factorial on that. Okay, so now I think we're ready to come up with our full Taylor series. We figured out what the pattern is there in the numerator. Now let's use this function here at the top of the page to build the entire Taylor series. All right, so f of x, remember that's 1 over x squared, is going to be the sum as k goes from 0 to infinity of the kth factorial evaluated at -1 over k factorial, all of this times x minus our a value, which is -1, then raise that to the k. I think we can clean this up just a little bit. We know that in this numerator here, the kth derivative of -1, we just determined that pattern is simply k plus 1 factorial. Of course, that gets divided by k factorial, and then we multiply by x minus -1, well, that's plus 1 raised to the k. I can simplify this just a wee bit more. I know that k plus 1 factorial is k plus 1 times k factorial. And then I also see that we can reduce out those k factorials. That's kind of nice. So we end up with f of x, which is 1 over x squared, is equal to the sum as k goes from 0 to infinity of k plus 1 times x plus 1 raised to the k. Now, what's really nice about this, there we go, ta-da, there it is. The beauty of this is in what we have. You'll notice what we started with was a rational expression, but what we ended with over here, this is polynomial. Okay, granted, it's an infinite polynomial, but it's still a polynomial, which can be much easier to work with than a rational. So that's the beauty of it. Enjoy!